Have you ever wondered what happens when something from another star wanders too close to our sun? Not a planet, not a spacecraft, but a traveler born under a different sky, carrying the chemistry of another world. Well, on October 29th, 2025, that's exactly what happened. The interstellar object known as 3I Atlas suddenly brightened 5 times brighter, in fact, as it swept through its closest approach to the Sunday. And that's the mystery. What could have switched on out there, in that furnace of light and gravity? The data is striking. The brightness curve climbs sharply, then steadies. Spectra reveal a strange mixed nickel outweighing iron, barely a trace of water, and an odd signature in the polarization of its light. Yet, there's no great plume of gas or dust to explain it. No visible debris, just an increase in radiance, clean and silent, as though something within the comet itself awakened for a moment and then faded again. You see, that's what makes this so compelling. Every number, every photon, feels like part of a message we're only beginning to decode, a reminder that even now, the cosmos still surprises us. Perhaps it's all natural, the play of heat and mineral, or perhaps it's a glimpse into a kind of matter shaped far from home. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So, let's continue. When 3I Atlas passed its closest point to the Sun on October 29th, something remarkable happened. Its brightness surged not gradually, not subtly, but in a sudden, almost theatrical way, multiplying by 5 within just a few hours. To anyone watching the live photometry streams, it was as if someone had turned a cosmic dimmer switch, flooding space with light that should not have been there. Telescopes from Chile to the Canary Islands confirmed it. The object, an interstellar traveler, had come alive. But what did that mean? What does it mean, in physical terms, for a rock or an icy fragment to brighten in the heat of the sun? You see, brightness, in astronomy, is never just brightness. It is a story, a trace of matter, motion, and temperature. When a comet glows, it does so because sunlight reflects off dust grains or scatters through gases released from its surface. The rule of thumb is simple. The brighter it gets, the more material must be flowing away. For 3I Atlas to shine 5 times more intensely, one would expect a storm of dust, a roaring jet of gas, perhaps even a visible coma expanding outward like smoke from a fire. Yet, when the images came in, there was nothing of the sort. No great plume, no spreading cloud. The space around the nucleus looked calm. It was the first paradox the light increased, but the evidence of what caused it did not. Astronomers began to retrace every piece of data. The photometric curve, that quiet heartbeat of numbers, told a precise story. A sharp rise centered on perihelion, then a slow decay over the following hours. The light was real. Instruments from independent sites confirmed the calibration. No filter errors, no software artifacts. So the question became deeper. How can something brighten without shedding matter? In the ordinary world of comets, brightness is linked to loss. Dust and vapor erupt as sunlight warms volatile ices, carrying away energy and mass. The more intense the outflow, the more light we see. But 3I Atlas refused to play by those rules. Even after the flare, high-resolution images from multiple observatories showed only a faint envelope, too small to explain the radiance. It was, as one researcher put it, a glow without a body. And that, well, makes one pause. Perhaps the brightening came from something internal, a sudden change in reflectivity, or a rearrangement of the surface itself. Imagine a crust, long frozen in the dark between stars, suddenly cracking open as it meets the furnace of the Sunday. Beneath it, minerals long sealed away might sublimate or oxidize, altering the way sunlight scatters from the surface. In that instant, the comet could flash like a mirror catching light. But even then, to sustain a 5-fold increase would require a large-scale transformation, kilometers of crust brightening in unison. That's not impossible, but it stretches our comfort with what we consider natural. Another idea followed, one rooted in the physics of geometry. When a small body spins, the sunlight it reflects can vary dramatically depending on the orientation of its surface. If 3I Atlas happened to rotate so that a particularly reflective face turned toward the sun near perihelion, its apparent brightness could surge without any change in material output. But this too would leave a signature, a periodic flicker, a rhythmic modulation in light as the body turned. Yet, the data show a smooth, continuous curve, no such rhythm. Whatever happened, it wasn't just a trick of orientation. So, what remains? A burst of heat? A hidden reaction within its metallic grains? The observations hint that 3I Atlas may be unusually rich in refractory materials, those that can survive high temperatures, like nickel and iron. But to make such metals glow visibly, they must be heated to thousands of degrees, far beyond what sunlight alone could achieve. And that's when you start to feel the gravity of the mystery. Every comet near the sun carries a tension between heat and time. The closer it flies, the faster it moves, and the shorter the window in which sunlight can act. 3I Atlas moved through perihelion at over 200 kilometers per second. A blink, really. So, whatever caused that brightening had to happen fast, within the span of a human afternoon. Imagine that. A traveler from another star system, moving at a speed no human craft could match, briefly flaring brighter than physics predicted, and then vanishing back into the glare. Some astronomers tried to fit the data into known patterns. Maybe the flare came from phase effects, where the scattering of sunlight increases sharply as the viewing angle narrows. Or maybe fine dust, microscopic, almost invisible, was released in just the right way to reflect more light per unit mass. But both of these explanations fell short when matched with the measured polarization of the light. The pattern of polarization told a quieter truth. The light wasn't dominated by fine, fresh dust. It was smoother, more metallic, more coherent. And so the paradox deepens. To shine brighter, the object must emit or reflect more light. To emit more light, it must either lose matter or become more reflective. Yet, the data show no great loss, no expanding halo, and no rotation pattern consistent with changing geometry. The conclusion, if you can call it that, is unsettling. Something happened near the sun that we don't yet understand. Perhaps we are seeing the interplay of materials not common in our solar system. Nickel-rich grains can undergo transitions that alter their albedo when heated, momentarily changing how they scatter light. On Earth, metals like nickel and iron can oxidize in milliseconds under intense heat. On an interstellar fragment, untouched for eons, those reactions could play out differently, quietly, without flames, producing light through microscopic rearrangements. And yet, that's speculation. We need more data, always more data. You know, what I find humbling is how these questions echo older ones. Centuries ago, comets were seen as omens, their light mysterious and unmeasured. Now, with every pixel of CCD data, we strip away that mystery, and yet, somehow, the mystery grows. Because each time we measure more precisely, we uncover something unexpected. 3I Atlas may be only a fragment of rock and ice, but it has already reminded us how incomplete our models are, and that's the essence of science, isn't it? You don't chase answers, you chase better questions. The paradox of brightness without evidence of dust is not just a puzzle about a single comet. It's a reminder of how small our sample of the universe truly is. 2 interstellar visitors, in a decade, each unlike the other, already suggest that typical may not exist beyond our system. In the coming weeks, as the object recedes and the glare of the sun fades, the data will sharpen. Perhaps a delayed dust cloud will emerge, faint but telling. Perhaps nothing will. Either outcome carries meaning. If the cloud appears, the mystery dissolves into physics. We can model the flow, estimate the loss, and adjust the timeline. But if it doesn't, if the brightness remains detached from mass, then we may need to rethink how light itself behaves around such exotic bodies. It's fascinating, isn't it? How a few stray photons can open entire worlds of thought. Somewhere, at the intersection of light, motion, and chemistry, lies the truth of what happened to 3I Atlas that day. But we're not there yet. We're still piecing together the clues, the acceleration data, the spectral lines, the dance of light and shadow that will tell us not only what brightened, but why. And that, well, leads us naturally to the next question. Because after the light, there was motion. The comet didn't just shine, it shifted, subtly but measurably, as if something inside it had begun to push. The light was only the beginning. After the light came the movement. Subtle at first, almost invisible, hidden in the scatter of data points and the hum of orbital equations. But once the noise was stripped away, the pattern became clear. 3I Atlas had changed its course. Not dramatically, not in the way a spacecraft might fire its thrusters, but enough that the numbers no longer fit the clean curve of gravity alone. Something else was at work. Something had pushed it. You see, every object in the solar system dances to the same music, the pull of the sun, the whispers of the planets, the faint drag of radiation. Those forces are predictable, calculable, elegant. But when astronomers reconstructed the post-perihelion orbit of 3I Atlas, the fit was off. It wasn't where gravity alone said it should be. The residuals, those tiny differences between prediction and observation, began to grow in a way that couldn't be ignored, and the only explanation was a force not caused by gravity. Before its closest approach, everything had been quiet. No sign of jets, no hint of outgassing, no measurable acceleration beyond the solar tide. But after October 29th, the object seemed to awaken. Two new components of acceleration appeared, one directed roughly away from the sun, the other tracing along its orbit as if something were gently pushing it forward. Curiously, there was no force acting out of the plane of its motion. It was all perfectly aligned with the geometry of its path. That alignment was the first clue. Natural comets, when they erupt, usually behave with a certain randomness. Gas vents open where the sunlight strikes, spin redistributes the flow, and the resulting acceleration dances erratically from one observation to the next. The pattern of thrusts tends to be messy, diffuse, ever-changing. But 3I Atlas, well, it behaved differently. Its non-gravitational acceleration was smooth, coherent, and remarkably stable. As though it wasn't just venting, it was following a plan written by its own orbit. Astronomers plotted the data again, this time comparing it with classic comet models, the Marsden law, the standard thermal models that predict how sublimating ices push a nucleus. None fit perfectly. The intensity of the acceleration was too strong to be explained by the faint gases expected at that distance from the sun, yet its direction remained steady, almost geometrically perfect. The implication was either a surface reacting uniformly or a kind of physics we hadn't seen before in such visitors. Some speculated it could be rotational. If the nucleus was spinning, and if that spin were locked to its orbital motion in just the right way, the outgassing could average into a steady push. But that would require a very particular orientation, and for an interstellar object tumbling chaotically through space, that's a big coincidence. Others wondered whether solar radiation pressure, the gentle push of sunlight itself, could be responsible. But again, the numbers didn't quite work. The acceleration was stronger than what sunlight alone could provide, unless 3I Atlas had an extraordinarily low density, or perhaps a broad, reflective surface, like a sail. And that, you see, is where imagination meets caution, because as soon as you mention sails and light pressure, people's minds leap to ideas that are far ahead of the evidence. The scientific discipline is to stay within what the data demands, no more, no less. Still, it's hard not to feel that stirring of wonder, that quiet question: what kind of material, what kind of structure could respond to sunlight so efficiently, so precisely? When you plot the acceleration vectors against time, a beautiful simplicity emerges. The force stays confined within the orbital plane, split neatly between the radial and tangential directions. No component rises out of plane. No irregularities break the pattern. It's as if 3I Atlas was being guided not by chaotic jets, but by a geometric rule, something intrinsic to its motion. In the old days, astronomers might have called such a thing self-propelled, not in the sense of intent, of course, but in the sense of a body reacting consistently to an internal process. Maybe the surface chemistry evolved rapidly after perihelion. Maybe volatile pockets opened symmetrically along the equator, creating balanced outflows that mimicked precision. Whatever it was, It left the signature of order where randomness was expected. And that's the kind of elegance the universe loves to hide in plain sight. Chaos that, when seen from the right angle, becomes pattern. Perhaps 3I Atlas was never chaotic to begin with. Perhaps its spin axis and surface structure were simply tuned by the journey between stars, refined by millions of years in interstellar radiation. In that light, its stability might not be mysterious at all. It might be the outcome of deep time. Still, the question of energy remains. To produce acceleration of that magnitude, something had to release power not much by terrestrial standards, but significant for a body only a few hundred meters across. If the gases involved were scarce, as the spectra suggest, then what supplied that power? One possibility is that sunlight, absorbed unevenly, caused local expansion within metallic grains, generating microjets of vaporized metal compounds. Another is that 3I Atlas carried minerals capable of storing energy in metastable forms, releasing it when heated past a threshold. In both cases, the physics would mimic propulsion, brief, steady, and planar. There's also the tantalizing idea that the shape of the object itself might have amplified the effect. If its body were elongated, like a shard or a flattened disk, the balance between radiation pressure and thermal emission could create a self-stabilizing thrust pattern. It would be, in effect, a natural solar sail not by design, but by geometry. Nature, after all, has no shortage of artistry. As the data accumulated, teams from observatories in Hawaii, Chile, and Spain began to compare their measurements. The consistency was striking. Independent reductions all showed the same trend. No pre-perihelion acceleration, then a clean, two-component push after the pass. It was as if something within the object had switched on quietly, precisely at the moment of greatest solar heating. That timing is crucial, because it means whatever mechanism drives the motion is tied to proximity to sunlight, temperature, or both. Before perihelion, the energy wasn't enough to awaken it. After, it was. Which brings us back to that phrase, switched on. It isn't poetic exaggeration. It's an honest description of the data. Perhaps then, the light and the motion are two sides of the same event. The brightening we saw wasn't just a change in reflectivity. It was the visible consequence of a deeper reaction, one that also produced the thrust. Maybe the material that caused the sudden flare was expelled just thinly enough to be invisible, yet powerfully enough to alter the orbit. A skin of fine vapor, unseen against the solar glare, could do the job. Or perhaps a rearrangement of surface grains changed both the scattering of light and the balance of forces. I like to think of it this way. 3I Atlas came in quiet, dark, and inert. It slipped through the inner solar system like a shadow. Then, as it met the full intensity of the sun, something inside it responded not explosively, but elegantly. It turned light into motion. For a few fleeting days, the laws of physics wrote a subtle choreography across the heavens, and we were lucky enough to witness it. But science doesn't end with beauty. The challenge now is to verify. To take this pattern, the smooth, planar acceleration, and test it against every known mechanism. Does it fit sublimation models if the surface is metallic? Could radiation pressure explain it if the density is ultra-low? Are there ways to distinguish these effects with future observations? Each possibility must be weighed, challenged, and, if necessary, discarded. This is where the work deepens, because while the photometric curve shows us brightness, and the orbital data reveals force, neither tells us what the object is made of. For that, we must look into the spectrum, the light scattered and emitted by its surface and gas. There, in the fingerprints of color and wavelength, lies the key to composition, temperature, and chemistry. So the story continues. The equations describe how 3I Atlas moved, but not why. To understand that, we must turn to the light itself, to the elemental whispers hidden in each photon, nickel, iron, carbon, cyanide, and perhaps something we've never seen before. And that, well, leads us naturally into the next chapter, where the mystery shifts from motion to matter, from the dynamics of its journey to the strange and beautiful spectrum it left behind. When the telescopes turned their eyes from motion to light, the puzzle deepened. Spectroscopy, that quiet art of splitting light into its colors, became the next frontier in understanding 3I Atlas. For in the subtle arrangement of those lines and bands, the universe writes its autobiography. Each wavelength corresponds to a fingerprint of an element or molecule, a trace of what the object is truly made of. And in late October, as the flare of 3I Atlas was still fresh, those fingerprints revealed something almost unsettling. Nickel. Far too much nickel. More, in fact, than iron, a reversal of what we expect in nearly every comet and asteroid studied before. The nickel-to-iron ratio, normally steady across the solar system, was inverted. And that, you see, is extraordinary. Because in cosmic chemistry, iron is the workhorse. It condenses first, it dominates meteorites, it anchors the cores of planets. Nickel, though similar, is rarer, a companion element that usually follows iron's lead. For 3I Atlas to show the opposite suggests a history far removed from anything our sun has forged. The data came in gradually, filtered, through instruments at different observatories. At first, the lines were faint, lost in the glare of the Sunday. But as the object receded and the glare subsided, the pattern emerged strong emission features around the wavelengths, associated with neutral nickel, weaker iron lines, and almost no sign of common volatiles like water vapor. The expected H2O bands, those familiar fingerprints of ice sublimating in sunlight, were nearly absent. Only 4% of the mass, at most, could be attributed to water. Instead, there were metallic vapors, strange ratios, and a scattering profile that hinted at coarse, reflective dust. It's tempting, of course, to jump to conclusions, to imagine exotic compositions, to picture some alien metallurgy, but science demands patience. The first question is always, could this be an error? Could the instruments, heated by proximity to the sun, have distorted the readings? Could scattered light have masked certain lines or enhanced others? That's why multiple teams worked independently, using different telescopes, different detectors, even different calibration stars. And remarkably, the trend held. Nickel was dominant. Iron lagged behind. You might wonder why that matters. After all, both metals are born in the hearts of stars, forged in the same supernovae that seeded the galaxy. But their balance tells a story about temperature, condensation, and the environment in which an object formed. In our solar system, the iron-to-nickel ratio is consistent because the nebula that birthed the planets was well mixed. For an object to deviate so strongly, it must have formed in a region with different cooling rates, or under pressures where nickel condensed but iron remained gaseous. In other words, it comes from a world with a different thermodynamic fingerprint, and that's what makes interstellar visitors so precious. They're samples of distant chemistry, fragments of other suns. 3I Atlas, in its brief passage, is like a page torn from a book written in another corner of the galaxy. To read it properly, we have to compare not only its elements, but the proportions: nickel to cyanide, iron to carbon, water to everything else. And in doing so, another anomaly emerged: a surprisingly low abundance of cyanide, that bright blue tracer common in comets. In most comets we know, cyanide glows vividly, betraying the presence of organic molecules broken apart by sunlight. Here, it was faint, almost ghostly. Taken together, low water, low cyanide, reversed metal ratios, the composition of 3I Atlas seemed almost dry, almost barren. A comet stripped of its volatiles, a nucleus of metallic and refractory material. That's strange for an object showing such brightness, for volatiles are what usually power the show. It's as though the curtain rose on a performance of light and motion, but behind the stage there was no fuel left to burn. And perhaps that's the heart of the mystery. If not water and carbon compounds, then what drives its glow? What produces its jets and its faint acceleration? One possibility is that 3I Atlas belongs to a class of bodies we've barely glimpsed, fragments of planetesimals whose outer layers were baked away long ago, leaving behind a crust of sintered metal and silicate. Under extreme heating near the sun, such materials can release trace gases like carbon monoxide, nickel vapor, or even sodium. These don't create the wide, flowing tails of ordinary comets, but can still scatter sunlight efficiently, producing a subtle, metallic radiance. There's also the chance that the spectral lines themselves are hinting at something dynamic, not static composition, but active transformation. Nickel, for instance, can evaporate from the surface when temperatures exceed 1,000 degrees Kelvin. At perihelion, 3I Atlas may have reached that threshold, shedding a whisper of vaporized metal into space. That vapor, glowing under solar radiation, could account for the unexpected brightness without requiring vast amounts of dust or water. In essence, the comet's surface might have briefly turned into a thin metal mist, shimmering in sunlight. It's a haunting image, isn't it? A wanderer from another star, heated by our sun, exhaling nickel vapor like breath in cold air. For a few hours, it glows brighter than ever before, then cools, falls silent, and drifts on. But as always, before wonder comes verification. Spectral data, especially near the sun, are notoriously delicate. Instruments must contend with glare, diffraction, and thermal interference. So the rule is clear. 1 measurement means curiosity, 2 mean interest, 3 mean evidence. That's why the community is now waiting for more for post-perihelion spectra from observatories farther from the sun, where interference is minimal. Only then will we know if the nickel lines were real, or if they were ghosts of reflection and noise. Still, there's a pattern forming. The polarization of light, measured just days later, seems to support the metallic picture low polarization angles, consistent with larger, smoother particles, not the fine icy dust of ordinary comets. And this, in turn, matches the spectral hints. The evidence, though incomplete, begins to cohere. 3. I Atlas appears to be a body of mixed metals and rock, unusually poor in ice, and yet capable of brief, powerful activity when heated. I suppose what fascinates me most is what this implies about time. Interstellar space is not kind to fragile things. Icy comets that wander for millions of years between the stars are gradually stripped by radiation and micrometeoroids, leaving only the toughest materials behind. If 3I Atlas truly lacks volatiles, then it may have been traveling for eons older than the sun itself, a relic from an ancient planetary system long gone cold. Every atom on its surface has endured 1,000,000 collisions with cosmic rays, 1,000,000 years of darkness, until this one encounter with our star awakened it. You can almost feel the history radiating from it. That brief flare of nickel light was not just chemistry, it was memory. A record of formation, destruction, and rebirth, written in the ratios of metals and the absence of water. It's strange, but comforting in a way, to think that even in such cold, silent fragments, the past of distant stars still glows. And yet, there's caution in every conclusion. Astronomers remind themselves daily that measurement is fragile. A small calibration error, a thermal gradient across a mirror, even a misaligned slit can mimic abundance anomalies. So the focus now shifts to replication, to observing 3I Atlas from multiple vantage points, using different spectral ranges, from ultraviolet to infrared. Only by comparing those views can we be sure of what we're seeing. If the nickel lines persist, if the water remains absent, then the result will stand. This kind of work is slow, but it's the heartbeat of science. The early data may be messy, the errors large, but the questions they raise, those are priceless. What kind of interstellar environment breeds such chemistry? Could this be the norm for other stellar nurseries? Or is 3I Atlas an outlier, a singular relic? And, perhaps most intriguingly, how does its composition influence the way it interacts with sunlight, with gravity, with space itself? There's a beauty in not knowing, in standing at the edge of understanding and realizing that beyond lies something utterly new. Each time we catch a visitor like this, we glimpse another version of planetary history, another chemistry, another narrative of formation. And that's what keeps astronomers awake at night, or, perhaps, dreaming with their eyes open. Soon, the attention will turn from the composition to the way that composition manifests in the texture of its dust, in the way it scatters light, in the strange polarization patterns that whisper of shape and structure. Because if the spectrum tells us what 3I Atlas is made of, the polarization tells us how it is made, the geometry of its grains, the architecture of its reflection. And that, well, is where the story naturally leads next. If the spectrum tells us what Three-Eye Atlas is made of, polarization tells us how its light is born, how it interacts with dust, with surface, with geometry. And, you see, that's where the story becomes tactile. Light is not merely color, it has direction, alignment, vibration. When sunlight bounces off grains of dust or scatters through a cloud, its electric field becomes oriented, polarized, depending on the size, shape, and composition of those grains. By measuring that alignment, we can, in a sense, feel the texture of the comet's dust without ever touching it. For most comets, the pattern is well known. The degree of polarization rises with distance from the sun, peaks at certain scattering angles, and always remains positive, meaning the light waves prefer to vibrate in a plane perpendicular to the scattering direction. This is what we expect when sunlight reflects off irregular particles of ice and rock. But in the case of Three-Eye Atlas, the readings began to whisper something different, something few had seen before: strong, negative polarization. Negative polarization means that the direction of alignment flips. Instead of light vibrating perpendicular to the scattering plane, it vibrates parallel to it. That's rare, and it usually appears only under very specific conditions when the scattering particles are large, smooth, and perhaps metallic. Observing such a signal near perihelion, when the comet's environment is turbulent and hot, was both astonishing and perplexing. It was as if Three-Eye Atlas was coated in dust that behaved less like powder and more like glass or polished stone. Now, polarization data are subtle things. They require precise calibration, control over atmospheric interference, and, crucially, observations from multiple angles. Because polarization changes with geometry, one telescope alone cannot tell the full story. So teams in different latitudes began to coordinate, measuring the scattered light as the comet moved through the inner solar system. When those results were combined, a clear pattern began to emerge. The polarization curve dipped into negative values more strongly than almost any comet on record. You might imagine this as light being folded back upon itself, like a reflection caught between two mirrors. It suggests that the grains near the surface of Three-Eye Atlas were either unusually compact or coated with materials that reflect coherently, perhaps metal oxides or dense silicates. If that's true, then the comet's brightness spike and its smooth, planar acceleration begin to make sense together. Both could arise from a surface dominated by large, compact grains, the kind that scatter light efficiently and respond uniformly to solar radiation pressure. But there's more to polarization than composition. It also speaks to structure, to the way particles clump and align within a dust cloud. In most comets, the dust is chaotic, a turbulent mix of tiny fragments and fluffy aggregates. The light they scatter is highly varied, producing only gentle polarization. For Three-Eye Atlas to show such strong and consistent negative polarization, the dust must have been unusually ordered, as though the grains were arranged or formed through a process of sintering and reformation, perhaps triggered by intense heat near perihelion. It's a little like seeing the difference between a cloud of smoke and a field of frost, one diffuse, the other crystalline. That idea leads to an intriguing possibility. Imagine the surface of the comet being heated to the point where metallic vapors, nickel, sodium, maybe even magnesium, briefly condensed and resolidified as the object moved away from the sunday. Those recondensed grains could have smooth, glassy exteriors, capable of reflecting light in that coherent, negative polarization way. If so, the polarization we measure isn't just a property of existing dust, it's a signature of transformation, of birth. We would be seeing, in real time, the creation of a new surface under the hammer of solar heat. And perhaps, well, that's what makes this so profound. 3. Atlas may not simply be showing us what it was made of, it may be showing us what it's becoming. Every close pass to a star reshapes such bodies, fusing and refining their surfaces, sealing some pores while opening others. The polarization pattern, then, becomes a kind of fingerprint of change, recording how a traveler between stars adapts to its encounter with the sunday. Of course, the scientists are careful. Polarimetry, as elegant as it is, can be treacherous. Tiny errors in subtraction or calibration can create illusions of strong polarization. Atmospheric dust, moonlight, Even reflections within the instrument can mimic or dilute the signal. That's why independent teams must check each other's work using different wavelengths, from visible to near-infrared, and from multiple viewing angles. Only when all those measurements align can we trust the pattern. Still, the data so far are consistent enough to intrigue even the cautious minds. The polarization phase curve of 3I Atlas dips below zero, then climbs again at higher angles, a shape that hints at both large grain size and a smooth refractive index. In essence, the dust particles are behaving less like the fluffy aggregates of typical comets and more like compact reflective pebbles. It fits, strangely well, with the story told by the spectrum, a surface rich in metals, low in volatiles, with chemistry more akin to rock than ice. If we accept that picture, then the light of 3I Atlas carries not the shimmer of gas, but the gleam of solid surfaces, perhaps relics of a planetesimal's crust, stripped and hardened by cosmic radiation during its long interstellar journey. The negative polarization becomes a clue to its ancient past, a signal of survival. What we see as an anomaly might simply be endurance, the mark of material that has outlived its softer cousins, crossing between stars like a fossil from another epoch. And yet, there's something haunting in that image, because negative polarization is, in a way, light's refusal to behave, a subtle inversion of the rules we take for granted. When light from our sun encounters such material and chooses to vibrate the wrong way, it's as if it's telling us, this place does not follow your norms. It belongs to another history. You know, perhaps that's what draws people to these studies, not just the pursuit of explanation, but the quiet awe that comes from watching nature break its own patterns. A comet that shines too brightly, moves too cleanly, polarizes too strongly, each one is a whisper of complexity in a universe that still has secrets to share. But the story of polarization also reminds us of perspective. Because these effects depend so heavily on geometry, the way we see them changes with our position, our wavelength, even the time of day. To truly understand what's happening around 3I Atlas, we need a network, a symphony of eyes across the planet, observing from every angle, every color, every atmospheric window. Only then can we reconstruct the full three-dimensional behavior of the dust, the interplay between light and motion. It's a humbling reminder that even in the age of space telescopes, we still rely on collaboration, on the patient knitting together of data from Earth. The next step, naturally, is to compare this behavior with other known comets to see if any share even a hint of this peculiar negative polarization. There are a few rare examples, like the bright sun grazers that shed metallic dust under extreme heat, but none match the amplitude seen here. It suggests that either 3I Atlas has a uniquely reflective surface, or that its dust contains some compound we haven't fully modeled yet, perhaps alloys of nickel or iron with other metals formed under alien conditions. If that's true, then every photon of polarized light we measure is not just a clue, but a conversation between our sun and a relic of another star, between the familiar and the foreign. And in that exchange lies the essence of astronomy, distant objects teaching us about the universality and diversity of physical law. Soon, attention will turn to imaging to the visible shapes and patterns that polarization alone cannot reveal. Because while the polarization tells us about the grains, the tail and the jets tell us how those grains move, how they interact with sunlight and magnetic fields. And, as it happens, 3I Atlas has one more surprise to waiting there, a tail that does not behave as it should, a structure that seems to point not away from the sun, but toward it, and that, well, is where our journey next leads. When the first images of 3I Atlas's tail began to circulate, they brought both excitement and unease. The early frames showed a structure that seemed to defy one of the simplest visual rules of cometary behavior. The tail, that elegant plume of dust and gas, was not pointing away from the sunday. Instead, to many observers, it appeared to tilt slightly toward it, as if some invisible wind were blowing in reverse. To those familiar with comet dynamics, it was a quiet shock. The tail is supposed to be a consequence of solar radiation pressure, of charged particles streaming outward from the sun and pushing dust into long, glowing arcs. So what, then, could bend it the other way? At first, the anomaly seemed almost like an illusion. Cometary tails, after all, are delicate three-dimensional structures seen in projection against the sky. A shift in viewing angle, or a change in the phase between the Sun, the comet, and the Earth, can make a tail appear to twist or even fold back upon itself. Astronomers know this trick well. Sometimes, what looks like a defiant gesture toward the Sun is simply the geometry of light and perspective. Yet, even after accounting for these factors, the images of Three-Eye Atlas retained their mystery. The inner tail seemed to fan toward the solar direction, faint but distinct, like a stream of material flowing inward against the solar tide. You see, the behavior of a comet's tail is not just aesthetic. It's a dynamic record of physics, the balance of forces acting on dust grains, plasma, and charged ions. Normally, there are two main components: the dust tail, curved and broad, and the ion tail, narrow and straight, driven by the solar wind. Both point away from the Sun, one gently, the other sharply. For Three-Eye Atlas, however, early spectroscopy suggested that the dust might consist of unusually heavy particles, perhaps even metallic grains, as we saw, from its polarization and spectrum. And heavier grains respond sluggishly to radiation pressure. They don't get pushed as easily. That, perhaps, could explain why part of the tail seemed misaligned. It wasn't truly pointing toward the Sun, but lagging behind in a geometry that made it appear reversed. Still, that explanation doesn't fully settle the question, because the tail of Three-Eye Atlas wasn't simply less deflected, it carried a faint ray, a thin, bright filament, directed almost sunward. Observers in southern latitudes caught glimpses of it near twilight, a narrow beam tracing the comet's inner region. Such a feature is extraordinarily rare. And when it does appear, it often speaks of something deep within the comet's rotation, a localized jet, or a sculpted surface feature directing material along a very specific path. To understand this, imagine the nucleus of Three-Eye Atlas as a rotating, irregular body, full of ridges, vents, and pockets of volatile material. As sunlight heats one region, gases escape, carrying fine dust with them. If the object is spinning, those jets sweep around, forming arcs and spirals that merge into the broad tail we see from Earth. But if the rotation and the shape align in a certain way, a jet can maintain a nearly constant direction in space, creating the illusion of a fixed ray. If that direction happens to be toward the Sun, it challenges our intuition but not the laws of physics. It's not that material is flowing inward, it's that the source is oriented in such a way that the emission angle fools the eye. Some have suggested an even subtler explanation: magnetic or electrostatic effects. As the comet approaches the Sun, its surface becomes electrically charged by the constant bombardment of solar particles. In regions of complex magnetic fields, this can momentarily deflect small charged grains along paths that don't follow the usual outward flow. The result could be transient features, filaments, or streaks that seem to reach back toward the Sunday. They don't last long, but they add texture and mystery to the light we capture. And, there's something poetic in that how light, dust, and magnetic fields can weave illusions across millions of kilometers, creating patterns that seem to rebel against cosmic order, when in truth they reveal it. The comet's strange sunward ray, then, is not an act of defiance but a dance of geometry, temperature, and time. Still, the most cautious astronomers hold to the principle of verification. Before declaring any tail to point toward the Sun, they demand time series imaging, a sequence of photographs taken over hours, even days, to watch how the feature evolves. If it maintains its direction while the comet rotates, that would confirm a true structural asymmetry, not just a trick of perspective. And so, as Three-Eye Atlas moved away from perihelion, a coordinated campaign began. Telescopes across the southern hemisphere trained there, lenses on the fading glow, capturing its motion every few hours. Each image was a frame in a cosmic film, tracing how the rays shifted and whether their apparent sunward tilt persisted. Preliminary results were, once again, ambiguous. The ray faded quickly, suggesting a brief outburst rather than a stable jet. Yet, for that short time, it held its geometry. It didn't twist or disperse the way dust tails usually do. It was narrow, stable, like the beam of a flashlight through fog. If such a feature truly existed, it might mark a unique structure on the comet's surface, perhaps a ridge or a deep fissure that opened suddenly under solar stress. When sunlight hit that cavity, volatile gases trapped inside could escape in a narrow stream, carrying bright particles that scatter strongly in the sunward direction. One astronomer described it beautifully. It's as if the comet exhaled and the breath caught the sun's light before fading. That, I think, captures the essence of comet. The ray may have lasted only hours, but those hours tell a story of transformation, of heat and release, of ancient ice surrendering to the warmth of a new star. And perhaps this is where 3I Atlas begins to teach us about resilience. Most comets, after such close encounters, fragment or vanish. But this one endured, shedding only a little, changing only slightly. Even its misbehaving tail, that fleeting sunward gesture, was part of a larger equilibrium, a body holding together under stress, finding balance between forces that could have torn it apart. When you look at the images, though, what's striking is not just the physics, but the beauty, the way the tail curves like a brushstroke of light across the black canvas of space. You can almost feel its motion, the constant negotiation between push and pull, between sunlight and gravity. And in that delicate balance, perhaps, lies the true story of 3I Atlas. It's important, too, to remember that what we see from Earth is always filtered through perspective. A three-dimensional structure projected onto two dimensions can deceive us. Tails that seem to cross or bend may, in truth, be separate layers of dust, moving at different speeds, like veils overlapping in the wind. Modeling these illusions requires not just mathematics, but intuition, a kind of empathy with light itself, understanding how it travels and transforms across the void. Some researchers are now building simulations, feeding in the data from spectroscopy, polarization, and dynamics to recreate what 3I Atlas's environment might have looked like near perihelion. The early results suggest a complex choreography, heavy grains forming a short, dense core of dust close to the nucleus, while lighter particles, possibly ionized, extend outward in more conventional fashion. The apparent sunward ray could then be an optical intersection, the crossing of those layers viewed from our vantage point. In that case, the illusion is complete, and nature has once again reminded us of how easily the eye can be fooled by the geometry of space. Yet, even if it was illusion, it's still significant. Because illusions are data too, they tell us how light interacts, how our instruments respond, how the brain interprets what the cosmos offers. And sometimes, those illusions point the way to discoveries we might otherwise miss. So, whether the tail of 3I Atlas truly bent toward the sun or merely seemed to, it has already forced us to refine our models, to look again at the delicate forces shaping cometary behavior. It's a reminder that even the simplest phenomena, a tail of dust, can hold complexity beyond expectation. In a way, 3I Atlas has become a mirror for our understanding of comets themselves. It challenges the assumptions we carry, the easy stories we tell about what should be. The brightening, the smooth acceleration, the metallic spectrum, the strange polarization, and now, this puzzling tale together. They form a chain of questions, each linked to the next, none yet fully answered, but each leading us deeper into the heart of interstellar matter. And soon, the focus will shift again. Because to understand why 3I Atlas's tail behaves as it does, we must look at its orbit, at the plane of its motion through our solar system, and at how improbable its path truly is. For the next clue to its mystery lies not in its light or dust, but in its trajectory, in the thin sheet of geometry called the ecliptic, and in the strange statistics of objects that travel against the grain of our sun's motion. And that, well, is where our journey now turns. To understand the mystery of 3I Atlas, we must now step back, not just in distance, but in perspective. All the brightness, the motion, the dust, the rays, they are surface effects, temporary gestures. Beneath them lies something more fundamental, the path itself. The orbit of this visitor is the quiet geometry that tells the deeper story, the thread connecting all its strange behaviors to its origin beyond the stars. And when astronomers traced that path, they found something curious, something that whispered of both familiarity and improbability. You see, 3I Atlas moves in retrograde motion. It travels against the general flow of planets around the Sunday. While nearly all the worlds of our system drift counterclockwise when viewed from above the north pole of the ecliptic, this object cuts across their paths in the opposite direction, like a swimmer pushing upstream in a slow, immense current. Its inclination, however, is small, almost flat, relative to the plane of the solar system. That combination is unusual. Retrograde orbits tend to come in steep angles, plunging through the planetary plane like arrows from above or below. But 3I Atlas glides almost along it, a rebel that still follows the line of the others. Statistically, that's rare. The interstellar objects we've seen before, Oumuamua and Borisov, both came in at high inclinations, slicing through the ecliptic like cosmic tourists who didn't know the local traffic laws. 3I Atlas, by contrast, moves like a resident, as if it had known this celestial street before. Of course, that's only an impression, but impressions can be powerful. When numbers defy expectation, we search for meaning, and in that search, we risk creating stories the universe never told. So the challenge, again, is to balance curiosity with discipline. What are the odds of an interstellar body entering the solar system on a path so close to the ecliptic? Some estimates put it at less than 1 in 1,000. Yet, here it is, a visitor perfectly aligned with the planetary plane, yet moving backward through it. It's a coincidence, perhaps, but a striking one. And coincidences, well, they are both the delight and the danger of astronomy. They tempt us to see patterns where there may be none. Still, coincidences invite questions. How does such an orbit arise? One possible explanation is purely gravitational. The galaxy is not empty. It is filled with drifting bodies and clouds of interstellar gas. Over millions of years, these travelers are nudged and deflected by encounters with stars, planets, and even molecular clouds. Their paths bend and twist, and every so often, by sheer chance, one will wander into our solar system at just the right angle to mimic a member of the Sun's own family. 3I Atlas could be just that, a cosmic accident, a wanderer caught in a brief alignment of geometry. Another possibility is dynamical capture. Some models suggest that interstellar objects can be temporarily captured into the solar system's gravitational field when they pass close to massive planets like Jupiter. The probability is low, but not zero. Such an event could circularize the orbit slightly, flattening it toward the ecliptic plane before the object escapes again. If that were the case, 3I Atlas might have had a brief gravitational handshake with one of the outer giants before diving toward the Sunday. That encounter could explain both its flattened trajectory and the faint acceleration patterns seen after perihelion relics of an altered path. And yet, there is something statistically elegant about its orientation. Being close to the ecliptic means that, from our perspective, it is easy to observe. The geometry favors sunlight scattering and Earth-based tracking. It's almost as if the cosmos conspired to give us a clearer view. Of course it didn't, but it's tempting to think it did. The alignment allowed us to study its brightness in detail, to measure its polarization, and to record its tail structure from multiple observatories simultaneously. A less convenient orbit might have hidden these wonders entirely, so perhaps this coincidence, this improbable geometry, is also a gift. It reminds us that even random chance can create moments of clarity, opportunities to see the universe more deeply. 3I Atlas's path, improbable though it may be, has offered us a laboratory for testing our models of interstellar matter. And in that sense, the anomaly becomes not a question of why, but of gratitude that it happened at all. Still, for the scientific mind, gratitude is never the end of inquiry. We must ask whether its alignment with the ecliptic hints at something broader. Could it be that interstellar objects tend to follow certain galactic streams, and that the sun's own motion through the galaxy occasionally brings those streams into alignment with the planetary plane? If so, then perhaps 3I Atlas isn't an outlier, but part of a hidden population, a family of travelers sharing similar orbits, waiting to be found. The next decade of sky surveys may tell us whether this pattern repeats. When you think about it, the orbit of 3I Atlas is like a fingerprint of both chance and history. Every angle, every velocity component, every inclination carries The memory of past encounters, gravitational nudges from ancient stars, close brushes with other systems, perhaps even the birth motion of its parent star itself. By tracing its trajectory backward through space, astronomers can attempt to locate the region of the galaxy from which it came. But the uncertainties are vast. A single fraction of a degree of error in its measured velocity translates to light years of uncertainty across millions of years of travel. And yet, the effort continues, because somewhere in those vectors may lie a clue to the environment that created it, a stellar nursery rich in metals, perhaps, matching the nickel-heavy composition we've observed. It's humbling, isn't it? How a few numbers describing an orbit can connect us to such grand scales, from the quiet arc of a comet around the Sun to the swirling motion of stars within the Milky Way. The orbit is, in a way, the bridge between the small and the vast, and every time we measure one with precision, we're not just mapping movement, we're mapping history. But this precision also warns us against temptation. The fact that 3I Atlas's orbit appears unusual does not mean it must be extraordinary in origin. Statistical outliers are inevitable when you're dealing with billions of stars and trillions of trajectories. The mind loves patterns, but the universe loves probability. So, the proper scientific attitude is both humility and curiosity to note the anomaly without worshipping it. This is what distinguishes discovery from speculation. It's easy to see strangeness and declare it unique. Harder, but truer, is to hold the tension between wonder and doubt. That tension is where science grows. Perhaps 3I Atlas is simply a statistical oddity, one data point among many. But if, after we discover dozens more interstellar visitors, this pattern retrograde yet near the ecliptic repeats, then we will have something deeper, a window into the dynamics of the galaxy itself. You know, when I think of this object's orbit, I imagine it as a thread weaving through two worlds, the orderly plane of our solar system and the vast, chaotic ocean of interstellar space. For a moment, it crosses our stage, then vanishes again, carrying our questions with it. In that brief intersection, all our instruments, all our theories, all our curiosity converge. We measure, we calculate, we speculate, and for a heartbeat of cosmic time, we understand something larger than ourselves. But the orbit is not just about geometry, it's about probability and the psychology of how we interpret chance. Our species has always looked for meaning in the rare, the improbable. We see faces in clouds, patterns in noise, stories in stars. In a way, that's the same instinct that drives astronomy, the need to make sense of the improbable. 3. Atlas's near-ecliptic retrograde path tempts us with narrative, the idea that perhaps it's not random at all, that there's some deeper structure to the arrival of interstellar visitors. Maybe one day, with enough data, we'll know. For now, though, it remains a mystery poised between accident and design. Its orbit, like its composition, seems to exist in a space between categories, not quite comet, not quite asteroid, not quite anything we've seen before. And perhaps that's what makes it beautiful. It refuses to fit. It drifts where the probabilities are thin, reminding us that even in a universe governed by law, there is always room for surprise. As 3I Atlas continues its slow retreat from the Sun, astronomers will refine its trajectory with each new observation, reducing uncertainties, tightening the arc. The more we know about its orbit, the more we can infer about its mass, its density, and the forces acting upon it. The curve of its path holds clues to the way it interacted with sunlight and gravity, clues that might even help resolve the earlier mysteries of its sudden brightening and acceleration. And soon, those orbital calculations will lead naturally to the next question. How does the light curve, the measured rise and fall of its brightness, connect to the mass it might have lost during that near-solar encounter? Can we reconcile the brightness we saw with the apparent lack of dust? For that, we must turn from geometry back to light, from the grand scale of motion to the intimate physics of reflection and emission. The orbit tells us where it's been. The light curve will tell us what it left behind. And that, well, is where we'll go next. When astronomers turned their attention from geometry to brightness, they found themselves confronting a quiet paradox. The orbit of 3I Atlas had been measured, its strange alignment mapped, its acceleration noted, but the light curve, that delicate graph of brightness over time, still held unanswered questions. The brightness had surged near perihelion, brightened fivefold, and then slowly faded. Normally, such a flare would point to a violent release of material, ice sublimating, dust streaming away, sunlight catching in the mist of expelled particles. But, as the telescopes revealed in the days that followed, there was no such cloud. The coma, that misty envelope surrounding active comets, was small, faint, and surprisingly clean. It was as though the light had increased without a matching loss of mass. And that, you see, is not supposed to happen. In the physics of comets, brightness is almost a proxy for weight loss. When the nucleus sheds material, the increased surface area of dust and vapor scatters more sunlight, producing the glow we see. The more luminous the curve, the more substance must be evaporating into space. So, when the light of 3I Atlas rose so dramatically, the equations demanded that vast quantities of material must have been expelled. Yet, when astronomers looked, the evidence wasn't there. No great halo of particles, no heavy plume, trailing behind. It was a ghostly flare light without substance, energy without clear cause. To make sense of it, researchers began calculating what should have been. Using standard comet models, they estimated how much mass must have been lost to create that much light. The numbers were sobering. Even assuming highly reflective dust and efficient scattering, the comet should have shed tens of thousands of tons of material within a few hours. The absence of such a cloud meant one of two things. Either the particles were far larger than expected, reflecting more light per unit mass, or they escaped in a way that hid them from our instruments, perhaps in directions we weren't looking, or at wavelengths we didn't observe. It's a humbling reminder that even the best telescopes show only part of the truth. We see what light chooses to reveal, and light, like memory, can be selective. One possibility is that the dust grains released near perihelion were coarse, perhaps, millimeter-sized or larger. Such grains scatter light strongly but produce little visible haze. They would reflect sunlight like tiny mirrors rather than diffuse it like mist. If 3I Atlas expelled mostly large grains, the brightness would surge while the apparent size of the coma remained small. Moreover, those heavier particles would travel more slowly, staying close to the nucleus for days before drifting away, which might explain why no broad cloud was visible immediately after the event. Another idea is geometric, that the ejected material was directed along a line of sight where we couldn't easily see it. If the emission was concentrated along the comet's rotational axis, and if that axis happened to point partially toward Earth during the outburst, much of the escaping dust could have moved away from us, hidden behind the blinding central glow. In that case, the instruments would register brightness without being able to resolve the structure that caused it. It would be like looking straight into the beam of a flashlight, brilliant but featureless. Then there's the matter of wavelength. Most observations of 3I Atlas were made in the visible and near-infrared range, because that's where comets usually shine. But if the material it released radiated mostly at mid-infrared wavelengths, heat rather than light, the true energy of the event might have gone unnoticed. Some models suggest that metal-rich dust, especially nickel and iron grains, can emit strongly in the infrared without much visible glow. If that's the case, the apparent mismatch between light and mass could be a trick of our own limited vision. And, perhaps, that's the lesson here, that nature often hides in spectra we haven't yet looked at. The universe doesn't owe us its transparency. It reveals itself only in fragments. Still, even within those limits, the light curve of 3I Atlas tells a story of precision. The rise and fall of its brightness was smooth, almost mathematical. There were no chaotic spikes, no irregular flickers from fragmenting pieces. That steadiness suggests that whatever process drove the brightening was global, not local, a change affecting the whole surface rather than a few active vents. It was, in a sense, the entire object breathing in light and exhaling radiance, not an eruption but a transformation. To quantify that transformation, astronomers applied radiative models equations linking brightness to albedo, particle size, and thermal emission. Assuming a moderate albedo of around 0.1, typical for comets, the measured luminosity implied an illuminated area far larger than the visible nucleus. This discrepancy can be reconciled only if the surface reflectivity increased, perhaps as dark crust burned away to reveal fresher, metallic material underneath. If the perihelion heat stripped a thin layer of carbonized dust, exposing bright nickel and iron grains, the reflectivity could indeed have doubled or tripled, explaining much of the observed surge. In that view, the brightening wasn't caused by material leaving the surface, but by the surface itself changing, becoming a mirror for a brief moment under the furnace of the Sunday. I like that image, a cosmic mirror, forged in darkness, flashing once before fading again. It's both poetic and plausible, which is rare in science. There's also the thermal angle to consider. As the comet approached the Sun, its surface temperature likely exceeded 1,000 Kelvin, hot enough to alter mineral structures. Silicates can lose water, metals can oxidize, and the texture of grains can shift, changing how light scatters. Some materials, when heated, even undergo phase transitions that alter their emissivity. The brightness spike of 3I Atlas could, then, be the visible signature of such a transformation, the moment when the surface crossed a thermal threshold and temporarily reflected more efficiently. But even if these explanations hold, a puzzle remains. Why didn't we see a delayed release of dust afterward? In most comets, the heat absorbed near perihelion continues to drive outgassing for days or weeks, producing extended tails. Yet 3I Atlas quieted almost immediately. That silence is telling. It suggests that the volatile materials, the ices and organics that usually fuel such activity, were scarce or deeply buried. Once the outer layer stabilized, the light curve returned to its calm decline, fading as the comet receded from the Sunday. The brightening, it seems, was a one-time event, the awakening and resealing of a surface rather than sustained evaporation. Still, the absence of visible dust doesn't mean the object lost no mass. Even large grains, invisible in the glare, contribute to momentum exchange. The subtle non-gravitational acceleration observed after perihelion hints that material did leave the nucleus, just not in the familiar, showy way. The amount may have been small, perhaps only a few thousand tons, but enough to alter its trajectory and leave fingerprints in its orbital parameters. It's strange, isn't it, how much of astronomy is inference? We never touch what we study. We read patterns in light, in motion, in numbers. From those, we reconstruct stories about matter millions of kilometers away. 3I Atlas teaches us that those stories must remain flexible. When the light curve contradicts the physics of dust, we adapt, we test. We seek missing pieces in unobserved wavelengths. Science, after all, is not about certainty, it's about persistence. And there is persistence here. Even as 3I Atlas fades, the light curve continues to whisper clues about what might have happened at its heart. By comparing its post-perihelion fading rate with thermal models, we can estimate how much heat it absorbed and how efficiently it radiated it back. If the brightness falls more slowly than expected, it could mean the surface remains hot, perhaps still undergoing subtle chemical changes. If it fades quickly, it might mean the energy escaped almost instantly, confirming a reflective rather than emissive origin. Either way, each data point becomes a pixel in a larger portrait, the portrait of a body that blurs the boundary between comet and asteroid, between ice and metal, between what we expect and what we see. And perhaps that's the quiet beauty of it. 3. Atlas doesn't announce itself with drama or destruction. It teaches by contradiction. It reminds us that even when the models fit poorly, the universe remains coherent. We just haven't yet found the right parameters. In the coming months, as observations from space-based telescopes arrive, we may finally detect the faint thermal glow of those hidden particles, the infrared signature of dust too large to scatter light but too small to hold heat for long. If found, it would confirm that the comet did indeed lose mass, only in ways invisible to our eyes. If not, then we'll have to accept something more profound, that brightness, in this case, was an illusion of geometry and transformation, not a measure of loss. And that, well, brings us naturally to comparison. Because somewhere else in the sky, another comet, C 2025 K1 Atlas, made its own close approach to the Sun just weeks before. It too defied predictions, surviving the heat when it was expected to crumble, and emerging gilded with a golden hue. By placing these two travelers side by side, we may begin to see a pattern not of mystery, but of diversity, a spectrum of possible worlds within the same cosmic family. And so our gaze shifts once more, from one atlas to another, in search of what they share and what makes each unique. When the story of Three Eye Atlas first began to unfold, astronomers couldn't help but notice an echo in the data, a kind of cosmic symmetry. Just a few weeks earlier, another comet, C2025 K1 Atlas, had passed through its own perihelion on the 8th of October. Both carried the same name Atlas, not by coincidence, but because they had been discovered by the same Wide-Field Sky Survey, the Asteroid Terrestrial Impact Last Alert System, scanning the heavens for moving light. Yet what followed for each could not have been more different. K1 was expected to perish in its close encounter with the Sun. Its fragile nucleus should have disintegrated, scattering into dust as so many comets do. Instead, it survived, emerging with a strange golden hue that shimmered across the telescopic images like sunlight through amber. For scientists already puzzling over Three Eye Atlas, the coincidence was irresistible. Two comets, both marked by the same survey, both defying prediction, both shimmering in ways no model quite anticipated, one interstellar, one native to our solar system. Were they connected, somehow? Was there a deeper thread, a shared origin, or at least a shared physics between them? It is the temptation of the human mind to link the rare with the rare, to draw patterns from the unlikely. But, as always, nature resists our desire for easy symmetry. The two atlases, it turns out, are not twins but mirrors reflecting different aspects of the same cosmic process, illuminating through contrast rather than resemblance. C2025 K1, unlike its interstellar namesake, is bound to the Sunday. It orbits in a long, looping ellipse, a wanderer of our own system rather than a visitor from another. As it approached perihelion, observers prepared for disintegration. Its trajectory would take it dangerously close to solar heat, a regime where fragile ices and dust aggregates cannot usually survive. Yet, to everyone's surprise, K1 endured. Not only that, but as it rounded the Sun and re-emerged into view, it appeared transformed, its coma glowing with a soft metallic hue, a faint yellow gold unlike the bluish tones of ordinary comets rich in cyanide and carbon compounds. Spectral analysis soon confirmed what the eye had already sensed. The usual signatures of carbon-bearing molecules were weak, almost absent. The bright bands of Cn and C2 that dominate many cometary spectra were muted, replaced by subtle emissions from refractory materials. The color, that golden tint, came from a deficiency, the absence of those carbon compounds that usually fluoresce in the blue. In their place were the warm reflections of silicate dust and possibly metallic grains, scattering sunlight with greater coherence. The effect was less an addition than a subtraction, a glow born from what was missing. And that's the beautiful irony of science. Sometimes what is not there tells us as much as what is. The lack of carbon volatiles suggests that K1's surface, like that of Three Eye Atlas, may have been processed, baked, irradiated, stripped of its more fragile ingredients by long exposure to heat or cosmic rays. But unlike the interstellar traveler, K1 still carries the memory of its origin, within the solar system, a record of our Sun's own chemistry and its long evolutionary history. When you place their spectra side by side, the contrast is striking. Three Eye Atlas, with its reversed nickel-to-iron ratio and meager traces of water, seems metallic, alien, forged under conditions we can only guess at. K1, though lacking in volatile carbon, still shows the fingerprints of silicates and familiar dust grains. It is exotic, but not foreign, strange but not unknowable. And perhaps that is the lesson these two comets together impart. The universe is not divided cleanly between the familiar and the alien. It is a continuum, a gradient of histories, with each object occupying a unique point between chaos and order, between the known and the new. Still, it's tempting to see the two as a kind of dialogue. Where Three Eye Atlas teaches us about the durability of interstellar material, K1 speaks to resilience within our own system. Both passed close to the Sun, both faced conditions that should have undone them, and both survived, not unchanged, but evolved. Their light curves, though different in scale, share the same pattern of sudden brightening followed by calm decline. The same language of survival, written in photons. You know, it's moments like this that reveal the quiet poetry of astronomy. We are watching not just rocks and dust, but stories of endurance. K1 and 3 I Atlas are like two travelers who took different roads to the same destination, the Sun, and each emerged bearing the marks of their journey. One arrived from the depths between stars, older than our species, perhaps older than our planet. The other rose from the distant edges of the solar system, shaped by the same sun it now orbits. And both, in their own way, became brighter near the edge of destruction. There's something profoundly human about that, this idea that proximity to heat, to pressure, to endings can bring illumination. The universe seems to tell the same story again, and again, written in matter and light. But in the realm of measurement, poetry must yield to data. For K1, the golden hue and its spectral peculiarities have practical implications. The lack of carbon emissions means fewer radiative losses, allowing the comet's surface to retain heat more efficiently. That heat could lead to localized melting or restructuring, sealing cracks that would otherwise have destroyed it. In a paradoxical way, its deficiency in volatile materials may have saved it a dry, hardened crust, protecting the core within. It is a reminder that sometimes what seems lifeless or barren is, in fact, the condition for survival. Astronomers have begun modeling these effects, comparing K1's behavior to the interstellar 3 I Atlas. If K1's golden glow comes from silicate dust and refractory minerals, perhaps 3I's metallic spectrum reflects an even more extreme version of the same process. One forged in another stellar nursery, another star's light. The sun, in heating both, becomes a kind of equalizer, revealing through its fire what time and distance had concealed. And yet, there is caution here. To link the two too closely would be premature. Similarity in name and timing does not imply shared nature. The temptation to weave them into a single narrative must be resisted until the data confirm it. That's the discipline that keeps wonder honest. Each object must be treated on its own terms, its own evidence, its own uncertainties. Still, comparison remains one of the most powerful tools in science. By setting two anomalies side by side, we see the edges of our models more clearly. What one object lacks, the other might possess. What one exaggerates, the other tempers. Between them, a pattern begins to form, not a conclusion, but a map of where to look next. For both comets, color is the key. Color is the intersection of physics and perception, where temperature, composition, and geometry merge. The golden hue of K1 and the silvery gleam of 3I Atlas are not mere aesthetics. They are expressions of matter under stress, of surfaces reshaped by heat and radiation. They remind us that even in the vacuum of space, transformation is constant, and beauty often arises from the process of change itself. And, you see, there's something poetic about the way we study these transformations. We watch from 100 million kilometers away, gathering light that left the comet minutes ago, decoding it into tables and graphs, yet somehow, through all that abstraction, we feel closer to it than we do to many things on Earth. Perhaps because in those moments of observation, we glimpse our own reflection not in the physical sense, but in the persistence of matter, in the way both living and inanimate things respond to pressure with grace or fracture. The story of K1, surviving where it should have perished, challenges our assumptions about what comets can endure. It broadens the definition of resilience, and it helps contextualize the mystery of 3I Atlas. What if these two comets, so different in origin, are simply points along a broader spectrum of behavior, one bounded by ice and carbon, the other by metal and stone? What if the universe is telling us that there is no single archetype for a comet, no universal formula, only a vast diversity of materials, histories, and responses to heat? That idea, if true, could reshape how we interpret every future observation of such bodies. Instead of asking why one behaves differently, we may come to ask why we ever expected them to behave the same. And perhaps that's what makes this moment so exciting. The two atlases, bright against the twilight of 2025, are not mysteries to be solved but teachers to be listened to. They whisper that diversity is the rule, not the exception, that every object carries a unique record of its making, its journey, and its encounter with the Sunday soon. As the months pass and more data arrive, attention will shift again, because both 3I Atlas and K1 have now moved beyond perihelion into the cooler expanses where their after effects can be studied in detail. Spectroscopy, photometry, and polarimetry will reveal what remains, whether the dust lingers, whether new jets awaken, whether the brightness decays or stabilizes. And with those observations will come the need for verification, for systematic campaigns to test each hypothesis under the same light. The next step, naturally, is to build that framework to design a way of observing that leaves no ambiguity, no untested assumption. And that, well, is where our path now turns from wonder to method, from the stories of two comets to the discipline required to understand them both. After the twin atlases left their fiery encounters with the sun, astronomers turned from speculation to structure. It was time to test what could be known to move from marvel to method, because wonder alone, however luminous, fades, but data, when gathered carefully, endures. So the scientific community began to outline what they called the post-perihelion verification framework, a global campaign designed to find, within the fading light of 3I Atlas, the traces of what truly happened near the Sunday. The plan was simple in principle, but immense in practice. To combine multi-wavelength spectroscopy, high-resolution imaging, polarization studies, and precise orbital tracking into one cohesive effort. The goal was not to explain, but to measure, and to measure independently, to let the data, not the theory, speak first. You see, the moment after perihelion is when the secrets of a comet linger longest. The nucleus has survived its trial by heat, but its surface is newly scarred, reshaped, and reactive. Any remaining outgassing, any late bloom of dust or vapor, can reveal the chemistry and mechanics hidden beneath its crust. For 3I Atlas, that window was closing fast. Its speed was immense, and every day carried it millions of kilometers farther from the Sunday time. In this case, was not just money, it was meaning. The first component of the campaign was spectroscopy, spreading the light of the comet into its constituent colors, looking for faint molecular bands that might have been missed earlier. In particular, scientists were eager to detect delayed emissions, signs that sublimation continued after the main brightening had passed. Molecules like CN, CO, and OH, the usual suspects, might appear weakly in the ultraviolet and infrared, even if invisible in visible light. Their presence would confirm that material was still escaping, that the brightening was indeed tied to volatile release rather than pure reflection. Their absence, on the other hand, would push the narrative toward a metallic or mineralogical explanation, but spectroscopy alone cannot solve the puzzle. The second front was imaging not just ordinary photographs, but a carefully sequenced chain of high-resolution frames taken over many nights, ideally covering full rotational cycles. This is how astronomers search for recurring features, for the subtle jets or vents that repeat as a nucleus spins. If 3I Atlas released gas or dust in pulses, those patterns would reveal its rotation period and the location of active sites. Repetition is the key to causation. One flash can be coincidence, two or three, a cycle. Parallel to these efforts came polarimetric measurements. By observing the comet's light from different angles and wavelengths, teams hoped to trace how the polarization evolved as it moved away from the Sunday. If the strong negative polarization detected earlier persisted, it would confirm that the strange dust structure was real, not a temporary artifact of heat or geometry, but a genuine property of its grains. If it faded quickly, then perhaps it was a transient effect, a brief reshaping of the surface that smoothed out once the heat receded. Polarization is like a breasted fingerprint that fades with distance. It tells us whether what we saw near the sun was part of the comet's true nature, or just a performance under stress. And then there were the orbit measurements, quiet but essential. Even the smallest non-gravitational accelerations can hint at ongoing activity. If, in the weeks after perihelion, the trajectory of 3I Atlas continued to deviate from pure gravity, it would mean the nucleus was still venting material, however, invisibly. Careful timing of its position across multiple nights, using radar and optical astrometry, could detect accelerations as tiny as a few 10,000ths of a meter per second squared, whispers of momentum, exchanged from escaping gas. To those who listen closely enough, even the faintest shift can tell a story of energy and matter. The campaign also emphasized multi-angle and multi-wavelength coordination. No single telescope, however powerful, can see a comet in full context. Light behaves differently in each part. Of the spectrum, infrared reveals heat, ultraviolet shows chemistry, visible light captures reflection and scattering. Combining these views creates a kind of temporal stereoscopy, where each wavelength tells a different part of the same event. Coordinated networks in Chile, Hawaii, Spain, and South Africa began scheduling their nights, passing the baton of observation as Earth rotated. It was a collaboration as much about humility as about precision, an acknowledgement that understanding something truly cosmic requires more than one pair of eyes. What then were they looking for? Specific signatures, yes, but also patterns, correlations across instruments and times. A delayed dust cloud, faint but persistent, would confirm that the brightening was material in nature. A molecular band, emerging days after perihelion, would point to buried volatiles venting through new fractures. A repeated jet, modulated by rotation, would reveal structure beneath the surface. And if none of these appeared, that too would be data, perhaps the most intriguing data of all, suggesting that the brightening was purely reflective, born of surface transformation rather than loss. Some models even predicted the possibility of late-onset activity, a secondary flare triggered not by heat but by thermal lag. When the comet passed perihelion, its outer layers would have heated quickly, but the deeper material, insulated by dust and metal, would take days to catch up. When that deeper layer finally warmed enough to release its gases, the result could be a delayed outburst, a ghost of the earlier event, smaller but measurable. To catch it, telescopes would need to watch not just immediately after perihelion, but for weeks, even months, as the comet retreated. Patience, not intensity, would be the virtue here. And that patience, well, is what defines the scientific spirit. The temptation after an event like this is to rush to interpretation, to claim discovery, but the wiser path is slower to test every assumption, to separate what was measured from what was inferred. The post-perihelion campaign was designed exactly for that, to let the data breathe, to see which patterns hold when the heat of excitement cools. You might think of it as a kind of astronomical archaeology. The brightening was the eruption, the spectacle. The post-perihelion data are the ruins left behind. By studying those ruins, the lingering dust, the changing color, the small shifts in orbit, we reconstruct the event, not as spectators but as historians. And like all good history, it requires cross-checking sources, confirming details, and resisting the lure of a single narrative. There's also something profoundly human about this collective effort. Scientists scattered across continents, linked only by shared curiosity and the faint signal of an object millions of kilometers away, working in concert to decode its message. Each observatory captures a fraction of the truth. Only, when those fragments are joined, does the full picture emerge. It's an act of trust, of patience, of faith in the process. Perhaps that's why this stage, the verification, feels quieter but deeper. The initial flare of 3I Atlas was dramatic, yes, but drama fades. What endures is the methodical reconstruction, the slow accumulation of understanding. The real beauty of science lies here, in the humility of measurement. And yet, as the observations accumulate, there's a lingering uncertainty that no amount of data can entirely erase. What if, after all this work, the pieces still refuse to fit the model? What if the spectra remain anomalous, the accelerations too smooth, the dust too strange? What if, in short, nature refuses to be ordinary? That is the question waiting quietly beyond the horizon of this campaign. Because verification, when done honestly, sometimes deepens the mystery rather than resolves it. The more precisely we measure, the more clearly we see where our theories fail. And if, after all the measurements and the independent checks, 3I Atlas still defies our expectations, then we will face a choice: to expand our models of natural cometary behavior, or to admit that something in our assumptions must change. And that, well, leads us directly into the next phase, not of observation, but of interpretation. For once the data are in, the task becomes to weigh the hypotheses, to test which natural explanations can hold and which must fall away. It is the moment when numbers become meaning, when measurement turns to understanding. When the last wave of post-perihelion data finally arrived, the spectra, the light curves, the polarization tables, the orbital refinements, the time for measurement gave way to interpretation. The community had done what it could in the realm of observation. The comet had spoken in light and motion. Now it was our task to listen, to assemble meaning from fragments. And yet, as the numbers settled into place, the patterns that emerged were neither simple nor singular. 3. I-Atlas continued to resist easy explanation. Its data seemed to invite multiple interpretations, each incomplete, each carrying both promise and doubt. In the first meetings and papers that followed, scientists approached the analysis like archaeologists brushing dust from a half-buried artifact. The post-perihelion acceleration was real, small but persistent, and directed cleanly within the orbital plane. The polarization measurements still hinted at those large, smooth grains, even weeks after the flare. The spectrum showed a continued deficiency in volatiles, and the brightness declined more slowly than expected, as though some hidden process kept feeding the light long after the heat had passed. And when all these clues were placed side by side, 3 main hypotheses began to crystallize. None perfect, all plausible. The first was the reflective surface model, the idea that the brightening was not an eruption, but a transformation. In this view, 3I Atlas did not eject much material, it simply changed the way it interacted with sunlight. The heat of perihelion might have burned away a dark, carbon-rich crust, exposing fresh metallic minerals underneath nickel, iron, perhaps magnesium silicates. These would reflect light more efficiently, producing the surge in brightness without requiring mass loss. The smooth decline afterward would then represent gradual redarkening as the surface cooled and oxidized once more. The non-gravitational acceleration could be explained by the small amount of gas still escaping through microscopic pores, too little to form a visible coma, but enough to nudge the orbit. It's an elegant model, and elegant models are always tempting. It fits the numbers neatly, aligns with the spectra, and demands nothing exotic, yet it leaves a strange taste of incompleteness. For if the surface truly became more reflective, why did the polarization remain? Strongly negative, as if dominated by metallic dust? The reflective model predicts coherence, but not the peculiar scattering patterns observed. It explains the brightness, but not the texture. That gap led to the second idea, the coherent grain hypothesis. Here, the key was not surface change, but internal cohesion. The flare, in this version, came from the sudden release of fine metallic dust held together by electrostatic forces. Imagine a crust charged by solar radiation, its particles clinging like static on a balloon. As the sun's heat intensified, those charges reached a threshold and collapsed, releasing the grains in a single pulse. Large, smooth particles, rich in nickel, could scatter sunlight efficiently while producing the negative polarization signature, measured near perihelion. Because they were heavy, they would stay close to the nucleus, forming a compact, bright cloud rather than a diffuse coma. The event would look like a flare but would leave little visible trace afterward. This model captures the texture well, and it accounts for the polarization, the acceleration, and even the brief sunward ray that puzzled early observers. But it requires a kind of fine-tuned electrostatic instability, something possible, but not yet observed directly in comets. Laboratory analogues exist for dust in plasma environments, but whether a natural body could charge so uniformly, then discharge so suddenly, remains uncertain. Still, it's a tantalizing idea, one that bridges chemistry, physics, and the raw artistry of coincidence. And then there's the third explanation, the hybrid model. In this view, both surface transformation and dust release occurred, intertwined like cause and effect. The crust heated, fractured, and partially melted, revealing bright metallic grains beneath. Those grains, once freed, reflected light intensely and were pushed gently by sunlight, causing the post-perihelion acceleration. Over hours, the combination of reflection and fine particle release produced the 5-fold increase in brightness. The hybrid model is messy, but so is nature. It admits imperfection, embraces complexity. It's not as graceful as the reflective model, nor as novel as the electrostatic one, but it feels alive, dynamic, plausible, rooted in the real chaos of heat and matter. Still, each model carries its own philosophical weight. The reflective hypothesis whispers of endurance, a body surviving by adapting its skin. The coherent grain idea speaks of sudden release, a moment of tension giving way to revelation, and the hybrid, well, it suggests evolution, the blending of destruction and creation in a single gesture. It's strange how even in astrophysics, our theories end up sounding like parables. What unites all these ideas, though, is a recognition that 3I Atlas forces us to rethink what activity means in interstellar objects. We are used to comets behaving predictably, brightening through, sublimation, fading, as volatiles deplete. But here, the mechanism seems subtler, driven not by ice but by metal, not by evaporation but by reflection and restructuring. It's a kind of dry activity, a physics of surfaces rather than gases. If confirmed, this would redefine how we classify such objects. Comet might no longer fit. Active interstellar body might be closer to the truth. The debates grew lively in the months after. At conferences and in online forums, scientists argued over the fine print of each dataset, the slope of the light curve, the alignment of acceleration vectors, the faint anomalies in polarization angle. Some papers favored thermal alteration, others cohesive release. The disagreements were rarely personal, but they carried passion, that rare and beautiful mix of skepticism and wonder. You could feel, in those discussions, the same curiosity that once drove early astronomers to track comets by eye, drawing their paths against the stars. And, yet, through all that debate, a quiet consensus began to form on one point. Whatever the mechanism, it was natural. There was no need for exotic explanations, no call for speculation beyond physics. The data, though strange, lived comfortably within the realm of known processes: chemistry, radiation, electrostatics, thermal dynamics. The universe, as always, had surprised us, not by breaking its rules, but by revealing new ways to apply them. That humility that returned to natural law is the true triumph of science. Still, one cannot ignore the deeper resonance of it all. A traveller from another star, crossing our system for the briefest moment, flaring in light, teaching us that even the oldest matter can still transform under warmth. It's easy to get lost in the equations, but there's poetry there too. You might say 3I Atlas reminds us that nothing in the universe is truly inert. Everything reacts, everything changes, even in silence. Perhaps that's why these findings matter beyond their technical details. They stretch our imagination of what alive means in cosmic terms. Not biological life, of course, but a kind of dynamism, the way matter responds to energy, the way geometry and chemistry conspire to make beauty out of entropy. In a sense, every comet is alive in its own language, every reflection, a heartbeat in the story of creation. And you see, there's something comforting about that. To know that the universe is not static, but perpetually reshaping itself, surfaces, melting, grains, fusing, light scattering in patterns that never repeat. In studying comets, we study transformation itself. 3I Atlas just happens to be a clearer mirror than most. As 2025 draws to its end, the observations continue. A few late detections hint that the brightness is now nearly constant, suggesting the object has cooled and stabilized. Its journey outward, back into interstellar space, is almost complete. Soon it will be too faint for even the largest telescopes to follow. But the data it leaves behind, terabytes of light and motion, will keep scientists busy for years, refining their models, debating the ratios, searching for echoes of its behavior in other comets yet to come. And perhaps that is where this chapter of the story settles, not in certainty, but in continuity. The interpretation of 3I Atlas is not an ending but an invitation. It tells us that our understanding of interstellar bodies is still embryonic, that we are only beginning to learn how these fragments of other worlds behave under the touch of our Sunday. It also reminds us that discovery is never a single event, but a sequence: observation, verification, interpretation, reflection. Each phase feeds the next, looping endlessly, like orbits around a truth we may never fully reach. But to orbit a mystery is, perhaps, better than to solve it. Because as we circle closer, our questions grow more refined, our sense of wonder deeper. And just beyond the horizon of this inquiry lies another, the question of where such objects come from, what kind of systems forge them, and what they can tell us about the architectures of other stars. That, well, is where our attention now turns outward, to the galactic neighborhood that sent 3I Atlas on its long journey toward our Sunday. When the models began to fray at their edges, when the fits no longer fit as neatly as before, the tone of the discussion changed, not into speculation, not yet, but into something subtler, something almost philosophical. What happens when data persistently, quietly refuse to match what we think we know? That question, more than any single measurement, defined the next stage of the story. 3I Atlas had been observed, modeled, compared, debated, yet its brightness, its motion, its composition, all continued to lean slightly away from the familiar. And so, the community found itself at a crossroads, the one every scientific generation, eventually, faces, whether to stretch the model or to rewrite it. You see, in science, anomalies are not errors, they are invitations. Each one is a chance to learn not that the universe is stranger than we thought, but that our assumptions were smaller than its truth. For 3I Atlas, the problem wasn't chaos, it was coherence. Every dataset made sense in isolation. The light curve, the polarization, the acceleration, even the peculiar nickel lines. Each could be explained within natural physics. But together, they tugged in different directions. No single model could hold them all without a quiet unease. Some researchers began to argue that perhaps the very idea of a comet needed revision. Interstellar bodies, they suggested, may not fit our solar categories at all. In our system, we divide them neatly: icy comets, rocky asteroids, metallic fragments, but those boundaries are artifacts of our own neighborhood. In the vastness between stars, the chemistry and history of solids might be far more diverse. A body born in a different stellar nursery could be layered with minerals we've never seen coexisting before, its ices mixed with metals, its surface aged by radiation for 1 billion years longer than any comet here. If so, then our models of sublimation, reflectivity, and dust behavior might simply not apply. The puzzle would not be a mystery to solve, but a map to redraw. And yet, there were those who urged caution. The discipline of science, after all, rests on proportion between evidence and claim. Extraordinary explanations demand extraordinary proof. Before rewriting the textbooks, one must exhaust every ordinary option. There may still be hidden biases in the measurements, uncalibrated detectors, or assumptions buried in our data reduction software. A single overlooked constant can create an illusion of anomaly. The proper course, they said, was patience. More data, more cross-checks, more nights under the stars. Perhaps that's the most human moment in all of science, when patience and imagination meet in tension. We are creatures of curiosity, drawn to mystery like moths to light. But our greatest achievements come not from surrendering to wonder, but from holding it steady long enough to test it. As the months passed, new analyses arrived, each tugging gently at the boundaries of explanation. One team proposed that cosmic ray processing over millions of years could have hardened 3I Atlas's surface, creating a shell of fused metal oxides resistant to sublimation. Another suggested that the object's history of stellar flybys might have reheated its interior long ago, producing trapped gases that only partially escaped when reheated near our Sunday. These are not radical ideas, just careful extensions of natural physics. They stretch the model but do not break it. And yet, a few voices whispered something rarer. What if the physics itself needs expansion? Not in the sensational sense, but in the quiet, foundational way that once redefined how we think of comets as dusty snowballs rather than solid stones. Perhaps interstellar objects experience electrostatic effects that scale differently at high velocities. Perhaps their surfaces respond to sunlight in non-linear ways due to grain alignment or magnetic memory. None of these would violate known physics. They would simply extend its reach into a regime we've never studied directly. Every discipline has such moments when the tools of yesterday need one more decimal of precision to meet the truths of tomorrow. And, you know, that's the beauty of this uncertainty. It reminds us that science is not about having answers, but about earning them. A mismatch between model and measurement is not failure, it's the pulse of progress. 3i Atlas, by refusing to fit, is doing what the cosmos has always done, urging us to look again, to question gently, to wonder correctly. For the more reflective among the scientists, this phase carried an almost spiritual undertone. They spoke of humility, the kind that comes when data undo the comfort of certainty. The cosmos does not exist to confirm our models exist to approach the cosmos. And sometimes, the approach must change. Still, the discipline remains. No one leaps to speculation without cause. The principle of parsimony, the idea that the simplest sufficient explanation must take precedence, still holds. Until every natural pathway has been explored, alternative hypotheses must remain in the margins. That's the integrity of science, the refusal to mistake intrigue for evidence. But the frontier is widening. Already, researchers are preparing the next generation of instruments, survey, telescopes, and spectrographs designed to capture future interstellar visitors with greater precision. The hope is that 3i Atlas will not remain alone, that others will follow, each adding a data point to a population we are only beginning to define. If the next few such objects show similar behavior, brightening without visible dust, metallic spectra, stable planar, acceleration, then the pattern will speak for itself. A new class of bodies will have been found, and our theories will evolve accordingly. You can almost imagine it, a catalogue of interstellar travelers, each bearing the marks of its home system, each whispering its own version of how matter and light behave elsewhere in the galaxy. 3i Atlas may simply be the first that stayed long enough for us to notice. Perhaps, in time, we'll even learn to predict their arrival, not as surprises, but as invitations, moments when the galaxy itself reaches into our solar system to offer a fragment of its story. When that happens, our models will no longer be stretched by anomalies, they will have grown to include them. For now, though, we live in the space between knowing and not knowing. The data fit imperfectly, the models hold partially, the truth remains ahead of us, and in that space, that delicate tension, science thrives, because it's there, in the uncertainty, that imagination becomes method, and method becomes discovery. 3i Atlas, with all its contradictions, is more than an object. It's a conversation between evidence and expectation, between what we think the universe is and what it continues to show us it might be. If the data refuse our current models, that's not a wall, it's a door. The question is whether we have the patience to open it carefully. And that, well, leads us forward from the boundaries of explanation to the horizon of understanding, to the larger question of what diversity among interstellar objects might truly mean. If 3i Atlas is one among many, then what do the many look like? How varied, how ancient, how telling are the fragments that drift between the stars? The next step, naturally, is to explore that population, to map not just one traveler's story, but the family of wanderers that share the galaxy's interstellar highways. If 3i Atlas is not alone, then it belongs to something larger, a quiet, invisible population of travelers that drift through the Milky Way, ancient as dust. Unclaimed by any star, the discovery of one such body hints at many more, perhaps millions, crossing the spaces between systems in silence. And now, with the lessons of 3i Atlas still fresh, astronomers are beginning to imagine what that population might look like, what stories it might tell about the galaxy's hidden architecture. You see, every interstellar object carries a fragment of its birthplace. Its orbit, its composition, its behavior under sunlight, all are shaped by the conditions of the system that forged it. To trace their diversity, then, is to reconstruct a cosmic census, a record of the galaxy's creative habits. The first step in that reconstruction is to understand the scale of possibility. Our solar system, for all its grandeur, is just one node in a vast galactic web. Every other star likely has its own debris, planets, comets, asteroids, and over billions of years, gravitational interactions throw some of those fragments outward, ejecting them into interstellar space. Each ejected body becomes a messenger, carrying within its atoms the fingerprints of the world it left behind. The galaxy, in this view, is not empty, it's full of travelers. And yet, until recently, our instruments were too limited to notice them. The night sky was alive with movement, but our eyes were not yet sharp enough to see. Since the detection of the first known interstellar visitor, Oumuamua, in 2017, followed by Borisov in 2019, the statistics have been slowly shifting. 2 objects were enough to prove existence. 3, with 3, I-Atlas, began to hint at diversity. But to move from anecdote to understanding requires numbers dozens, hundreds, perhaps thousands. That realization is driving the next generation of sky surveys, from the Vera Rubin Observatory in Chile to space-based instruments designed to scan for faint, fast-moving bodies. Their goal is not just to find the rare and spectacular, but to catalogue the quiet multitude. And what might that multitude reveal? Patterns, perhaps. Some interstellar objects may resemble comets, shedding dust and gas near our sun. Others may remain inert, rocky, reflecting only faintly. Some might spin rapidly, others slowly. Some may arrive steeply inclined, diving through the solar plane like arrows from afar, while others, like 3 I-Atlas, might glide almost flat, tracing paths that suggest long histories of gravitational sculpting. In those patterns, we will begin to glimpse the mechanics of stellar systems far beyond reach, how planets form, how debris evolves, how matter circulates through the galaxy like blood through veins. It's remarkable, really, to think that the Milky Way may be filled with such wanderers. Each one is a fossil from another star's past, traveling for millions or even billions of years before crossing our sky. Some may be remnants of shattered worlds, fragments of planetary crusts or metallic cores. Others may be pristine, unchanged since the dawn of their own systems, bearing the chemical record of the nebulae that birthed them. Their diversity will not just broaden our knowledge, it will transform it. For the first time, we will be able to compare matter from multiple stellar nurseries directly to hold in our equations, if not yet in our hands, the chemistry of other suns. Of course, finding them is only the beginning. Once detected, each interstellar visitor must be tracked, measured, and studied before it vanishes again into darkness. Their velocities are immense, their windows of visibility short. 3 I-Atlas, for example, was bright for only a few weeks before fading beyond the reach of most telescopes. To study such objects effectively, astronomy must learn to move faster, to coordinate across continents, and wavelengths within hours, not days. In a way, the discovery of interstellar objects is as much a challenge to our organization as to our technology. The cosmos presents the data freely. It is we who must learn to listen in time, and that, perhaps, is the quiet revolution of this new era, a change not only in what we see, but in how we see. The science of the transient has become the science of the interstellar. We now design instruments to catch what vanishes, to extract meaning from moments. And through that practice, we begin to understand the fleeting as fundamental. Some researchers are already dreaming further ahead of missions that could intercept or even sample an interstellar body directly. The idea sounds audacious, almost impossible, but physics does not forbid it. If we can predict the trajectory of a future visitor early enough, perhaps months before it arrives, we could launch a probe to meet it, to photograph it up close, to taste the dust it carries from another world. Imagine that, material older than our sun, untouched by our solar winds, entering a capsule of human design. A handful of atoms that began their journey when Earth was still molten could, one day, end in a laboratory under our microscopes. The dream is bold, but every new technology begins as an act of audacity. And yet, beyond the technical ambition, there lies a quieter meaning. For the first time in human history, we are not just observing our own solar system, but sampling the galaxy itself, not through telescopes alone, but through physical messengers. Each interstellar object that enters our sky is a bridge between worlds, a reminder that the boundaries between systems are porous, that matter and light and gravity weave all stars into a single, connected fabric. Perhaps that's why 3 I-Atlas feels so significant, even beyond its data. It's not the largest, nor the brightest, nor the most perfectly understood, but it came at a moment when our eyes were ready, when we had the instruments, the patience, and the curiosity to notice. It turned abstraction into presence. We no longer speak of interstellar space as empty, we speak of it as populated, dynamic, alive. Still, with every discovery, new questions arise. If such objects are common, why have we detected so few? Are most too dark, too small, or too slow to notice? Does the sun's gravity capture them temporarily, as some simulations suggest, turning them into unseen guests, orbiting quietly within our system for centuries before leaving again? Could our solar system already host a dozen such visitors, hiding among the asteroids, indistinguishable from the natives except in their isotopic ratios? These are not idle questions. They are the beginning of a new field, the archaeology of the galaxy, conducted not with shovels, but with light. And, there's something beautifully circular about that. For centuries, we've looked outward, building larger telescopes to study distant stars. Now, the stars are sending fragments of themselves to us. It's as if the universe, in its own patient way, decided to meet us halfway. Statistically, the next few decades should reveal many more of these travelers. Some will pass silently, too dim to study in detail. Others may blaze briefly, like 3I Atlas, revealing chemistry and structure before fading. Each one will expand the boundaries of our understanding, forcing us to refine our models of formation, ejection, and evolution. And as the sample grows, we will begin to see not just individual stories but galactic patterns, correlations between metallicity, orbit, and behavior. From those we might infer the history of the Milky Way's disk itself, where heavy elements concentrate, where debris thrives, where planetary systems are most violent. That, perhaps, is the ultimate promise of this field, that by studying the small, we may glimpse the structure of the vast. Every pebble from another system becomes a pebble, data point in the map of the galaxy's memory. But alongside the scientific vision lies the emotional one. When you stand beneath the night sky and realize that a faint, fast-moving dot up there was born around another sun, it changes something in you. It makes the distances between stars feel smaller, not in measure, but in meaning. You begin to see the Milky Way not as a scattering of isolated lights, but as a single, breathing, organism stars, exchanging matter, systems shedding fragments, gravity, weaving them together like threads in a cosmic tapestry. And perhaps that is the quiet truth behind all this measurement and mathematics. We are part of that exchange. The same processes that send fragments toward us also send fragments of our system outward. Somewhere out there, far from our sun, a small rock ejected from the early solar system might be crossing another sky right now, catching the light of an alien star, being watched by someone else who wonders. The story of 3I Atlas, then, is not just about one comet. It's about belonging, about realizing that even the coldest, loneliest fragment of matter participates in a shared galactic story. And as we look outward, measuring the paths of other travelers, we begin to glimpse the web that connects us all. Soon, this search for interstellar wanderers will merge with another frontier, the study of exoplanetary debris disks and the chemistry of distant systems. By linking the compositions of interstellar objects to the spectra of those disks, we may begin to identify not just where these travelers came from, but which stars they once orbited. The galaxy will cease to be anonymous. Each interstellar object will become a messenger from a specific region, a named lineage, a story traced in light years and minerals. And that, well, leads us naturally to the next step, to look beyond motion and matter, and to ask what these messengers might reveal about the very origins of planetary systems themselves, about how worlds are born, destroyed, and scattered into the dark, carrying with them the seeds of new beginnings. The beauty of science, you see, lies not in its answers, but in its discipline, the slow, deliberate process of asking better questions. When we look back at 3I Atlas, at all the data gathered and all the uncertainty that still hangs in the air, what stands out is not the enigma itself, but the way we have learned to approach it. Each telescope, each night of observation, each cautious paper, all of it is a declaration of humility. We are learning, once again, that the universe is not obliged to make sense on our timetable. It reveals itself in whispers, and only to those who are patient enough to listen. The case of 3I Atlas is, at its heart, a reminder of the scientific ethos. The object brightened fivefold near the sun that much is certain. The light curves were real, the numbers checked and rechecked. Yet what caused that light? What switched on in that instant remains just beyond reach. The temptation, of course, is to fill that gap with speculation, to lean into the dramatic or the unknown. But science, when done properly, resists that urge. It stays grounded in what can be tested. Every extraordinary idea must earn its place by surviving the cold scrutiny of data. That is not cynicism, it's respect. Respect for reality, respect for truth, respect for the quiet honesty of the cosmos itself. And that honesty is often subtle. Perhaps 3I Atlas was simply a comet unlike any we've seen, metallic, dry, ancient beyond imagination. Perhaps it came from a system older than our sun, where chemistry and time sculpted matter into strange new forms. Or perhaps its behavior was entirely natural, a dance of geometry, reflection, and temperature, perfectly ordinary once understood. The truth may be less romantic than we hope, but that does not make it less beautiful. Because every refinement of our understanding, no matter how small, is a victory against ignorance. Every correction to our models, every discarded assumption, is a step towards seeing the universe as it truly is. What strikes me, and perhaps many who have followed this story, is how such a small speck of light can provoke such profound reflection. Think about it, a fragment, perhaps 100 meters across, traveling through the void for millions of years, happens to cross our sun's path in the year 2025. For a few brief hours, it brightens, revealing its chemistry, its motion, its defiance of expectation. And for those hours, the collective attention of our species turns toward it. Thousands of kilometers apart, scientists synchronize their telescopes, algorithms compare spectra, voices connect across continents, all to understand a flicker of light against the stars. That, to me, is civilization in its purest form, curiosity united by purpose. The data from 3I Atlas will outlive us. Stored in archives, analyzed and reanalyzed, it will continue to refine our understanding of interstellar matter. Perhaps in the years ahead, as new visitors are discovered, those numbers will gain new meaning. Patterns will emerge. What seems anomalous today may tomorrow become typical. Science advances not by final answers but by accumulating context, by turning mysteries into foundations. But until then, we live in a liminal space. The models of comets we have built over decades are strong, but not unbreakable. They have served us well, explaining the icy wanderers of our own system. Yet interstellar comets, these travelers from other suns, are forcing us to stretch those models to their limits. We may discover that the physics remains the same, but the inputs differ. Metals instead of ice, dust shaped by radiation instead of water vapor. Or we may find that something deeper must change, that the processes we once thought local to our system are, in truth, galactic. And well, that is the joy of it. Each unanswered question is a doorway, not a defeat. Science thrives on that tension between what is known and what is suspected. 3. Atlas challenges us not to despair at our ignorance but to delight in it, because ignorance is where learning begins. The discipline of skepticism, too, must not be forgotten. In the age of rapid communication, speculation can spread faster than evidence, yet real discovery demands slowness. It demands replication, cross-checking, independent verification. A single telescope's reading, no matter how striking, must be tested against others. Polarization data must be confirmed from multiple angles, spectra must be calibrated independently, orbital paths must be refined over time. This patience, this refusal to rush toward conclusion, is the foundation of scientific truth. 3. Atlas reminds us why that foundation matters. Because in the end, whether it turns out to be a rare comet or something entirely new, both outcomes are victories. If it fits within known physics, then we have proven the universality of nature's laws, that the same principles hold across stars, across ages, across space. And if it does not, then we have found a crack in the surface of understanding, a place where discovery will begin again. Either way, the horizon expands, and perhaps that's the real message here. Science is not a ladder leading upward toward perfection. It is a horizon, receding as we move forward. Each solution reveals new terrain, each explanation opens new questions. The universe, in its vastness, is not a problem to be solved but a conversation to be continued. You see, I think often about that light, the fivefold surge that lasted only hours. It was a whisper, really, a momentary shimmer in the glare of the Sunday. But in that shimmer was everything: physics, chemistry, history, wonder. It's humbling to think that light left the comet, crossed space, entered our atmosphere, struck the mirrors of our telescopes, and was transformed into data on a screen, and then into meaning in our minds. From dust and photons, we built understanding. From silence, we made story. That is the alchemy of science. There's also a quiet human truth woven through all this. Our fascination with comets and interstellar travelers is not just scientific, it's existential. They remind us of motion, of impermanence, of how even the smallest fragment can cross unimaginable distances. They carry the poetry of time. To study them is to confront the enormity of the cosmos and our fleeting place within it, yet also to realize that in studying them, we become part of their story. The photons that leave them touch us. Their trajectories, mapped and measured, intersect our own. In their passage, we glimpse continuity. As the last data from 2025 are processed, astronomers already look ahead. They plan for the next visitor, perhaps 4i, 5i, and beyond. The next object may be darker, slower, stranger. It may behave predictably, or it may again defy our expectations. Either way, it will arrive, as 3i Atlas did, unannounced. The universe will surprise us again. And when it does, the same questions will arise: how? Why? What does this tell us? That cyclical return of wonder is the heartbeat of astronomy. And yet, there's something more profound here, something almost personal. In following these fragments from other stars, we are tracing the same processes that once shaped our own world. The dust that forms comets, asteroids, and planets, it's the same dust that once swirled in the cloud that birthed Earth. Every interstellar object is, in a sense, a mirror of our own origin. To study them is to look backward in time, not just outward in space. They remind us that creation is not a singular event, but a continuous one, unfolding everywhere, always. Perhaps that's what the light of 3i Atlas really means. Not a signal, not a mystery, but a moment of participation, the cosmos, briefly showing us one of its endless expressions. We measured it, debated it, questioned it, and in doing so, we honored it. Because to seek understanding is itself an act of reverence. So, when we ask what switched on near the sun, perhaps the answer is simpler and deeper. It wasn't just the comet, it was us. It was the collective awakening of human attention, turning once more toward the unknown. That's what science does. It switches us on. It reminds us that curiosity is not a trait but a duty, a way of being alive in a universe that never stops offering questions. And that, I suppose, is where we leave 3i Atlas for now. The data continue to flow, the models continue to evolve, and our understanding will, in time, sharpen. Whether this object proves to be a strange comet, a metallic relic, or something else entirely, its gift has already been given. It has expanded our sense of possibility. It has reaffirmed the discipline of doubt, the patience of method, and the wonder of discovery. Soon, as the next interstellar visitor enters our sky, we'll remember this one, the light that flared near the sun in late October, the anomaly that invited humility. And when that new traveler comes, we'll be ready, better instruments, sharper eyes, deeper questions. Because that's what science does. It learns, it refines, it prepares. And so, to everyone who watched, who measured, who wondered, the story is not over. It continues outward, into the data still unexamined, into the hypotheses still unborn, into the next dawn, when another faint light will move against the stars, and we will once again ask the same timeless question: what just switched on near the sun? And well, that question, quiet, persistent, and luminous, will lead us forward into the next chapter, where wonder meets truth once more.